In this video, part of the Equipment of Diving series, I'm going to be looking at the stuff you need to know about tanks and valves. We're going to be looking at steel versus aluminium tanks. We're going to be looking at what you need to know about servicing. We're going to be looking at tank markings, and we're going to be looking at tank valves. So starting with steel versus aluminium. The greater strength of steel allows steel tanks to be made with thinner walls for the same equivalent working pressure. So this actually makes steel tanks of a comparable capacity lighter than aluminium tanks. So what do I mean by what's written there? Basically, if I wanted to have a tank that gave me a certain number of litres of air to breathe through, or cubic feet of air to breathe through, the steel tank, because its walls are thinner, would actually be physically smaller than the aluminium tank. These thinner walls have a significant effect on the tank's buoyancy characteristics. Since more air is being packed into a smaller space due to the steel walls being thinner, the steel tank is actually smaller. If the steel tank is smaller, then the volume of the water it displaces is less. That means, of course, that the weight of the water it displaces is less. And if the weight of the water it displaces is less, it will be more negatively buoyant. So this is quite a tough thing, I think, to get your head around. But what you've got to realize is that if you were to look at a steel tank and an aluminium tank with the same amount of air capacity, the same amount of air for you to breathe through, it would be visibly smaller. The steel tank would be visibly smaller than the aluminium tank. And as you hopefully know from studying the physics videos, the smaller it is, the less weight of water it displaces, the more negative buoyancy it's going to have. So, in fact, a steel tank would be physically lighter to pick up and carry down to the dive boat than an equivalent aluminium tank. But once the steel tank was in the water, it would now start feeling heavier than that aluminium tank because of the difference in buoyancy, because the steel tank is displacing less water than the aluminium tank. So when diving on an aluminium tank, you would actually need to wear more weight than if you were diving with a comparable steel tank, because the aluminium tank is more positively buoyant than the steel tank, even though they're both giving you the same amount of air to breathe through on the dive. So when completely empty, an aluminium 80 will be approximately 4 pounds positive. In fact, you may well have seen people, tossing used scuba tanks off the back of a dive boat at the beach and floating them back to the shore. And that's totally possible with an aluminium tank. However, a steel tank with the equivalent of air capacity of an aluminium 80 would probably be about 2.5 pounds negative, even when empty. So what you can see here is that when empty, an aluminium 80 would be approximately 6.5 pounds more positive than an equivalent capacity steel tank. So that basically means a diver using an aluminium tank would have to be wearing 6.5 pounds more weight than if they were to use a comparable steel tank. And not only that, of course, that that weight when it's in the tank, when you're diving with a steel tank, you've got it nicely spread out over your back, rather than the weight that you're wearing on a weight belt, for example, which tends to be all focused in one area. You need to be very careful about spreading your weights out so that you are properly trimmed. That might be taking some of the weights off your weight belt and putting them on ankle weights or in the pockets at the back of your BCD. This is less of a problem if you're diving with a steel tank. So during a dive, the weight change of both steel and aluminium tanks as you move from full to reserve pressure will be identical. The air that you've breathed through weighs the same, whatever type of tank it was contained in. So the change in buoyancy based purely on the air you've breathed through will be identical. It's the other characteristics of the tank that make the difference. Obviously, the big downside of steel tanks is their greater tendency to corrode in water, especially salt water. By this point, you might be asking yourself, why aren't we all using steel tanks if they're more negative, meaning we need to wear less weight, etc.? But when you're diving in salt water, the risk of oxidization, the formation of iron oxide rust on a steel tank is significantly greater. It tends to be significantly more of a problem than when you're using an aluminium tank. So tanks being used in salt water, people tend to prefer aluminium, although that's obviously not necessarily the case. A properly maintained steel or aluminium tank, you should be able to avoid the problem of oxidization. It's important to realize that aluminium tanks can also oxidize. You'd be getting aluminium oxide, which is generally a white substance, but it's less likely than with a steel tank. The process of making aluminium tanks involves heating and cooling them in a controlled manner to create a good tensile strength. So if an aluminium tank has been exposed to excessive heat, which is a heat greater than 350 degrees Fahrenheit, 177 Celsius, then that tank shouldn't be used. It should be sent for a hydrostatic test before further use. When you think about it, that sort of temperature, would be possible if it was even near a fire, let alone in one. So it's not inconceivable that a tank, you could realize, has become exposed to those sort of temperatures if the next door neighbor building burnt down or something like that. You'd have to seriously think about those tanks and send them for a hydro. So moving on to maintenance and servicing. There are two types of routine maintenance tasks with scuba cylinders. The first and most common is the visual inspection, which should occur yearly, at least every year, as a matter of routine. Most tanks will have visual inspection stickers on them, and when you're receiving a scuba tank to use, you want to have a quick look at that visual inspection sticker to see if it has been inspected within the last year. The visual inspection sticker will usually be something with months and years that sort of gets stamped. Hydrostatic testing should be done in accordance with local law. So different countries have different laws with regard to hydrostatic testing. The broadly accepted scuba norm is that a hydrostatic test should occur every 5 years. So let's look a little bit more at visual inspection. The annual visual inspection actually involves removing the valve from the tank. So you can check and inspect both the inside of the tank and the outside of the tank for damage. So the valve gets taken off and a light is usually inserted to be able to see the inside of the tank. And in that photo over on the right there, you can see that they're even using a mirror so that you can see the shoulder of the tank from the inside. What should you be looking for when you're doing a visual inspection? Well, firstly, you shouldn't be doing a visual inspection unless you've been trained in how to do a visual inspection. But those people who are trained in doing a visual inspection, they're looking for corrosion, oxidization. So this would be an example of a steel tank that has very severe corrosion, very rusty inside. You're looking for pitting, which is usually formed by oxidization as well. This would be an example of very bad pitting on the inside of a scuba cylinder. Also looking for cracks. Cracks are most likely to be found coming out from the neck, from the thread that the valve gets threaded into, and you'll see them up on the inside of the shoulder of the tank there, which is why it's so important to insert that light and use that mirror to look for these cracks when you're visually inspecting a tank. Dents most often commonly found on the outside of the tank through mishandling. And then the final thing is looking for galvanic action between the tank valve and the tank thread, or at least where the valve is in contact with the tank itself. Because galvanic action occurs when two electrochemically dissimilar materials are in contact and a conductive path occurs for electrons and ions to move from the one type of metal to the other type. So one metal corrodes as its ions are deposited onto the other metal. So for example, a brass valve in an aluminium tank, you have the possibility of galvanic action. Here is an example of what it might look like. So now let's look at hydrostatic testing. I'm going to go into quite a lot of depth in hydrostatic testing, more depth than you probably need to know, but I think it's helpful to fully understand it. So what we see here in this picture is that a scuba cylinder has been placed inside a hydrostatic test jacket. So the hydrostatic test jacket is full of water, the scuba tank is full of water, and then it is closed up and sealed. But what there is a small tube that allows the water of the water jacket to expand and come out, and if it does expand and come out, it will fill this little glass beaker you can see on the left hand side, which is placed on a scale. Before the test starts, the expansion 0 value is established. So what we see is that there is no pressure in the tank right now, and the scale is reading 0 grams. So the expansion 0 value has been established before any pressure is put into this tank in the pressure jacket. So then the tank is pressurized to the required test pressure for a required time. The test pressure is usually 150% of working pressure. So note that test pressure is way higher than working pressure. Test pressure is much higher than the pressure you would normally have this scuba tank filled to go on a dive. And filling it to this test pressure causes the cylinder to grow in size. Not really visibly grow, but you would be able to tell that the cylinder has grown in size because it will have actually forced water out of the test jacket and into our little glass beaker. So what we can see is that this tank is now under pressure, and the cylinder expansion at test pressure is recorded. So we would note down that 189 grams of water had come out of that test jacket into the beaker. You would then release the pressure that the tank is under back down to 0, and you would then have a look at the weight of the water that is still in that beaker. When the depressurized cylinder expansion is stable, a permanent expansion value is recorded. So the permanent expansion value of this cylinder in this test was 9.45 grams. Basically, there was 9.45 grams of permanent expansion. So in the example we just saw, the tank under pressure displaced 189 grams of water, and after the pressure was released, the permanent expansion was 9.45 grams. 9.45 divided by 189 would give us a 5% permanent expansion. As a general rule, anything less than 10% and the tank would pass its hydrostatic test. to summarize maintenance and servicing, visual inspections should occur annually. When else might you consider having a tank visually inspected? If you ever hear something rattling around inside the tank, obviously you shouldn't use it and you should take it to get a visual inspection. The most likely culprit is in fact the snorkel that you see here on this tank valve. That's something that actually unscrews from the valve. It's there just in case there was any water or oxidized metal, some sort of contaminant in the tank. If you were unaware of that and you went on a dive and you turned upside down, without that snorkel there, that contaminant would be able to go straight into the valve and straight into your regulator, possibly causing a fairly catastrophic failure. Also, if you feel the tank is heavier than normal, you shouldn't use it and you should get a visual inspection. The tank gets opened up, they have a look inside to see if there is something in there that shouldn't be. Most likely, obviously, an ingress of water, which would be obviously very dangerous and likely to cause corrosion on the inside of the tank, making it unsafe to both use and to fill. So the other type of maintenance or servicing that we discussed was hydrostatic inspections. These should be performed in accordance with local law, which is usually every 5 years. When else should you consider taking your tank to be hydrostatically inspected? Well, if there is an actual reason that you believe it has been damaged. That might be visual evidence, such as a dent on the outside of the tank, or it might be something that you know has happened to it, such as it's been dropped from a significant height, or it's been exposed to excessive heat. In those situations, you wouldn't even bother having a visual inspection. You'd go straight to hydro, because you are aware of something that's actually happened to the tank that may have caused it to lose its structural integrity, its tensile strength. Moving on to looking at markings now on tanks, starting with the markings you might find in a steel tank. Some of the most important ones to know about for the exams you're going to be taking are the metal type markings. 3A would denote carbon steel. This tank that we've got an example of here is 3AA, the more common form of steel now used to manufacture scuba cylinders. 3A stands for chrome molybdenum steel, quite a mouthful. Also, another interesting thing to know about, if you see a plus sign next to the hydrostatic tester's mark, that would mean that a 10% overfill of that tank is acceptable. So in this example, we see the working pressure above it is 2250. A 10% overfill would be acceptable. So maybe filling it to 2500 psi would be acceptable. And that is really the main things you need to know about the tank markings. The .CTC is a government agency approval, so this is obviously a US tank that can be transported across the border to Canada. You'd then always have a serial number, the information about the manufacturer on the tank. So aluminium cylinder markings, aluminium cylinders most commonly use, you'll see 3AL as the marking on the tank that tells you it's an aluminium cylinder. Although there could be other markings that denote either an aluminium or a steel cylinder. So whilst these are the most common things, the things that are likely to come up potentially in your exams, it's very important that you realize that tank markings do vary from country to country. So these tanks have to comply with local laws for transporting a cylinder of compressed gas on a highway. In one country, those markings might be different to in another country. So that is one of the main reasons that different cylinders in different countries may have different markings. Other markings that you might want to think about when you're thinking about tanks is the nitrox markings. They're obviously a nitrox tank needs to be marked as such, so it's not accidentally used by someone thinking it's air and taken to a depth greater than it should be used at. and taken and used by someone who's not trained to dive with nitrox. So a fairly typical nitrox markings you can see in this picture here, big yellow and green stickers. You'd also expect to see a visual inspection sticker on any tank. This is a visual inspection sticker where the month and year it was visually inspected would be punched out of the sticker before it was applied to the tank. You may well find an oxygen clean sticker on the tank. So basically, if the tank is oxygen clean, you would expect there to be an oxygen clean sticker, again showing the month and year that the tank had been oxygen cleaned. If you don't see one, then you can assume the tank is not oxygen clean. The other markings you would expect on a nitrox tank would be a label at least showing the blend, the max operating depth, and the name of the diver that had analysed it. More often you'll get more information than that: a cylinder number, the date, the pressure the tank was filled to, and maybe not only the maximum operating depth but a contingency depth as well. Very often duct tape is just used to meet this requirement, where you can write on with a permanent marker onto a bit of duct tape the blend, the maximum operating depth, your name or signature that you would fill in on it as you analyse it, and usually the date at least. So standard scuba gear can be used with nitrox blends up to 40% oxygen. You should always check the manufacturer recommendations, but usually you can assume that standard gear can be used with nitrox up to 40%. Using gear with a higher content of oxygen than 40% starts getting risky due to the risk of oxidation. Note that oxidation is different to oxidization. Oxidation is actually when the scuba equipment, the materials that equipment is made out of, might suffer from electron loss from the molecules they're made of as a result of being exposed to high levels of oxygen. So the scuba norm is up to 40% nitrox. We treat it pretty much as though it's air. Anything above 40% oxygen, the scuba cylinder needs to be oxygen clean, and we need to be absolutely certain that the scuba equipment we're using is safe for higher levels of oxygen. Moving on to valves, the standard scuba valve is called a K valve. It's a simple on-off valve that a single regulator can attach to. You may be asked questions about J valve. They're very, very dated now. In the past, before we had submersible pressure gauges to tell us how much air we had, a J valve would be used, and it would allow you to monitor your air in a very simplistic way. It utilizes a lever that is in the up position of the start of the dive, and when pressure drops to somewhere between 300 and 700 psi, the supply of air to the diver would be shut off. That would alert the diver that their air pressure is getting low, and they would then be able to reach behind them or use a J rod to move the lever back into the down position, allowing the remaining air to flow. So you can liken it to a reserve valve on a motorcycle gas tank, warning you that you're getting low on gas. So what it is a warning device to inform you when you are getting low on air. So looking at the internal workings of this J valve, if we see this valve attached to a tank, when we turn the valve on using the black valve on the side, air pressure flows, and it's able to flow up and push that spring that is the J valve mechanism out of the way, so air can flow out of the valve into the regulator. As pressure drops to say 5 to 700 psi, the spring that's part of the J valve mechanism now pushes the valve into closed, and air is no longer being able to be supplied to the diver, they would push the valve into the down position and allow the air to resume flowing again, knowing that they are getting to the reserve portion of the air they need to finish their dive and surface. So what other types of valve do we have? There are various different valves that might allow you to attach two regulators to one tank in case you have a regulator failure, or there is the dual manifold, which allows you to attach two regulators to two tanks. Let's have a little bit of a look at this one. It's an interesting one. Let's look at some of the features of it. So it allows a diver to breathe from both tanks evenly from either reg. It also allows either reg to be shut off if the regulator fails and starts free-flowing. So if the regulator failed and started free-flowing, let's imagine the regulator on the left-hand side fails. What we're going to do is shut off this valve here, and that will isolate that regulator. No more air will come from that regulator, but air will still be able to come from the left-hand tank to the right-hand regulator and allow you to continue breathing from both tanks, but now only from the right-hand regulator. Likewise, if the right-hand regulator failed, you would turn this valve and you would still be able to breathe all the air from both tanks using the left-hand regulator. What else might fail when you're using tanks? Well, it's less likely, but it is possible that there would be some sort of tank failure. Most likely the O-ring around the neck of the tank, where the valve goes into the tank, could fail, resulting in either a very significant fast loss of air from that tank, or maybe a slightly lower, slower loss of air from the tank. And at this point, you would obviously want to isolate that tank. So you would basically no longer be allowing the air to flow from the left to the right or the right to the left. So you would turn this valve, and now you are isolating the left from the right and the right from the left. The left-hand regulator can only get air from the left-hand tank, and the right-hand regulator can only get air from the right-hand tank. If this left-hand one was the one that had failed, the one that was leaking out of the neck O-ring, you would turn that isolator valve, and then what you would probably do is continue breathing off the left-hand reg until you had drained, used whatever air was remaining in that left-hand tank. And once you had no air at all, you would then be able to switch over to the right-hand reg and breathe through the air that's now in that right-hand tank, which doesn't have a leak. And all the while, you would obviously be following your emergency procedures to end the dive. Obviously, these are valves that are used in decompression diving more often than not, meaning that you can't immediately end the dive. You might well have to follow some sort of decompression schedule to get you out of Dodge. So moving on to look at burst discs or rupture discs. On the tank valve, you will find the burst disc. It relieves pressure from an overheated or overfilled tank. Obviously, if you don't have a burst disc that can do that, and you left your tank in a hot car, you might come back to find your car looking like this. Or if you were to leave a tank on a compressor that didn't have a proper overpressure release valve, and the tank didn't have a burst disc, your tank might end up looking like this. This was actually a very tragic story. This tank bursting did actually result in the death of one person, and another person lost their leg. So it was probably a multitude of problems, not having a proper burst disc and also not having a proper compressor that had a proper overpressure release valve. So the burst disc is designed to burst, to fail, and release air from the tank in a controlled manner at approximately 140% of working pressure. So this is what a burst disc actually looks like. It's that thin copper disc at the bottom of this picture, and it's held in place by that silver nut in the valve. what you can see is the silver nut in the valve actually has multiple holes on it. So if the burst disc bursts, it releases the air in more than one direction, which avoids the tank spinning when the burst disc bursts. The burst discs do need to be replaced regularly. They are usually replaced as part of annual servicing because they weaken over time, and they may rupture below working pressure if they are not replaced regularly. So how often should a burst disc be replaced? Regularly. So what have we looked at in this video? We have looked at steel versus aluminium tanks. We've looked at servicing. We've looked at tank markings. We've looked at different types of tank valves and burst discs.